This video is brought to you by Squarespace. Hi guys, welcome to Amateur Chemistry. So we all know vodka, right? It's this clear liquid that smells like danger and can make you lose your brain cells if you indulge yourself in it enough. Now, the chemical that makes all this happen is this little goober called ethanol. It's present in vodka as a roughly 40% solution in water, and apart from being able to obliterate your whole body, it has surprisingly many uses. Its chemical structure is really similar to this one, which in turn represents something called acetic acid, and it, also as a water solution, is what makes vinegar. Ever since I started learning chemistry, I have been really fascinated by how a tiny difference in chemical structure can drastically change the properties of a molecule, and this ethanol and acetic acid situation is literally the perfect example of this. For a long time, it was my dream to turn this deaf water into something that can be used for some delicious cooking, and on paper it actually seems like one of the most straightforward conversions on this channel. However, as these things always go, it isn't actually quite so simple, and selectively adding a single oxygen atom to an ethanol molecule to turn it into acetic acid is quite a chemical feat. Now, there are a few known methods to do this, each with its own set of challenges and quirks, and at first I didn't really know which one to use. The most well-known one involves the use of something called potassium permanganate, which is said to work quite well. However, I wanted my future vinegar to be the fruit of some substantial pain and suffering, and not a simple, boring reaction. Because of that, I dug deeper, and after a long Wikipedia surfing session, I came across a method that seemed almost perfect. It's something called the Jones oxidation, and from what I read, it's a really efficient and high-yielding alternative to all the other methods. What's even better, the ingredients and conditions required for it seem nothing but straightforward. One issue, however, is that it involves the use of one of the world's nastiest chemicals, which apart from being able to dissolve almost anything, just gives you cancer, and is the element of suffering I was so eager to introduce. This mysterious thing is of course chromium trioxide, which, as I've showcased in my last video, is a real pickle of a chemical. Now, I specifically wanted to use it since I've made it from some literal forks over the course of a few months, and using such a deadly and well-earned chemical to turn vodka into vinegar is nothing short of a poetic series finale. Okay, so with the overall method and goal in mind, I can now dive straight into turning vodka into vinegar using some forbidden pop rocks. However, first I would really like to tell you about the sponsor of this video, Squarespace. Squarespace is an all-in-one, advanced website creation platform for entrepreneurs to stand out and succeed online. Using it, you can create incredible websites with ease, whether you're just starting out or managing a growing brand, and use them to sell anything or promote your business. Squarespace gives you access to powerful features like their new Design Intelligence, which combines cutting-edge AI technology with 2 decades of industry-leading expertise to unlock your strongest creative potential and make your website tailored to your personal needs, which in my opinion is real cool. Additionally, Squarespace provides you with useful tools like their option for setting up donations to raise funds for your cause, which together with Squarespace payments that make checkout seamless to customers can make your business grow like never before. For a free trial, head to squarespace.com, and when you're ready to launch, go to squarespace.com/amateurchemistry to save 10% off your first purchase. Anyway, to cosplay some ancient alchemist, I can't just pour vodka onto chromium trioxide and expect to receive anything other than a sizable explosion. You see, chromium trioxide is a very angry chemical, to put it mildly, and while it can be used to perform a delicate oxidation like the one that turns ethanol into acetic acid, it first has to be fine-tuned so that it doesn't, for example, spray a mutagenic solution all over your fume hood. Now, before I start messing with chromium trioxide, I think that it's best to prepare everything else needed for the oxidation reaction in advance, because the second my chromium trioxide jar is opened, I begin to feel slightly uncomfortable. The best thing to start with will be ethanol, which I've decided to extract from vodka. I could in theory just use this 40% solution straight from the bottle, but the big amount of water and some unknown contaminants definitely won't help in taming the chromium trioxide. Extracting ethanol from vodka is quite a tricky task, and the main method usually employed is fractional distillation. It takes advantage of water and ethanol's slightly different boiling points and is the go-to method for any industrial ethanol production, but in the lab it has a few setbacks. The biggest one is that it's a big struggle to set up and run, requiring a sizable fractionating column to get a good enough separation, and from my experience, it's just not worth it on a scale I will be working on in this video. Now, there is a more novel and substantially more interesting method that exploits different solubilities of things in water. You see, when you add something like sodium chloride, or in other words plain table salt to water, it dissolves, making a solution, and when you keep adding more, the solution becomes saturated and unable to pick up any more salt. Now, if there was something else mixed with the water before adding salt, as the solution saturates, it should precipitate out since there is no more space for it to dissolve. In our case, the thing that should precipitate from vodka is some reasonably pure ethanol, which makes this whole procedure seem weirdly easy, and I was really eager to try it out. To start, I got this half-full bottle of vodka, from which I meticulously removed the label and replaced it with my designer one. I now had to measure out how much of it I want to use, which will dictate the scale of this whole project, and I've settled on 400 milliliters, which should both be enough to comfortably work with and require normal glassware instead of some plus-size flasks and beakers. To get my ethanol from this thing, I need to choose what salt I want to use, and since I remembered seeing somebody use just table salt to do this kind of stuff, I thought that since I have a ton of it, I might as well use it here. I weighed out 130 grams, which is roughly how much should dissolve in all my vodka's water, and then just kind of aggressively dumped it in all at once. I then proceeded to stir up this salty vodka and realized that this is the world's worst bartending tutorial, since drinking this nuclear concoction would be a hell of an experience. Anyway, even with some vigorous manual stirring, the salt didn't really want to dissolve, so I ended up having to use my hot plate's powerful magnetic stirring. Unfortunately, even it only got about half of the salt to dissolve, and there were still no signs of anything precipitating out. From what I read, this whole step should happen reasonably quickly and form a separate layer of liquid on top of the solution, both of which definitely didn't happen here. I was really surprised that this procedure didn't work, but because I've basically made it up using some common sense, I decided to research this topic a little more and found that common sense often doesn't make sense in chemistry. You see, the guy I saw do this indeed used table salt to separate alcohol from water, but he worked with a different alcohol called isopropanol, which is quite different from the ethanol I have to deal with. It turns out that for whatever reason, table salt just doesn't work for ethanol, and this felt like the chemistry gods were just messing with me, since after all this I had a bunch of really salty vodka and no real plan on how to go forward. I feared that I might have to resort to fractionally distilling this thing, but since I really wanted to use this salt-based technique, I researched it a little more and found that it does actually work, and you just have to use a different salt. The best one for this is supposed to be something called potassium carbonate, and I fortunately have a bit of it left over from an older project. Now, I have no idea if this is enough, but I decided to take a leap of faith and added about half of my potassium carbonate into the vodka beaker, and unlike table salt, it seemed to at least do something, at first making those cool waves appear. To help the carbonate dissolve, I again turned on magnetic stirring and left this now even more forbidden drink to do its thing for a few minutes. When I came back, a clear layer of what had to be ethanol started to form on top of the mixture, and I was amazed that just using a different salt made all this finally work. To get my ethanol from this beaker, I could either just decant it off or use a fancy separatory funnel, and I've actually settled on the funnel since it's a really cool piece of equipment and will allow for a more efficient separation. I poured the contents of my beaker into it, and I didn't quite manage to fit everything at once, but since the alcohol layer was on top, all that was left in the beaker was just some salty water. I now had to wait for the layers to separate again, which took quite a while and was weirdly satisfying to look at. When everything was ready, I drained away the lower water layer, which left me with what had to be some dirty ethanol. I also drained it into a beaker, and now it's time to purify it a little, since there is still some water and potassium carbonate in it, and the easiest way to do that is by carrying out a distillation. Now, I know that I seem to contradict myself here, since I've done this whole step to avoid distilling anything. However, the distillation I have to do now isn't nearly as complicated as the fractional one, and involves just boiling away most of the liquid without any weird steps in between. Anyway, before assembling the distillation apparatus, I wanted to take one last look at the water extract, since while it sat in my fume hood, I noticed something weird about it. You see, when liquids contain ethanol, this wave-like vapor often starts to form in their containers, and if my water layer didn't contain much ethanol, there wouldn't be those weird droplets appearing from seemingly nowhere on the sides of its beaker. What's even worse is that much like the supposed alcohol layer, it was rather flammable, meaning that for some reason it still contained a good amount of ethanol. This made me question my life choices and got me a little stirred up, because what was meant to be an hour's worth of work already took me almost a day. I fortunately still had enough patience to try extracting my ethanol one last time, and for that I first got the salty solution from before into the funnel to squeeze out any last bits of it. I got what had to be like 3 extra milliliters into my quote-unquote water beaker, and to force the water to stay as a separate layer, I dumped in a few grams of potassium carbonate. After letting it do its thing for a few minutes, I got this murky solution into the funnel again. This time the alcohol layer appeared quite a bit faster, and I prayed for it to not suddenly disappear or get magically turned into water. I got it into the large ethanol beaker from before, and I was sure that this still wasn't nearly as pure as I wanted it to be, since the maximum amount of alcohol I could have extracted from 400 ml of vodka is 160 ml, and the total volume of liquid in the beaker was around 200 ml. To get the water out of this thing once and for all, I got the beaker onto a hot plate and dumped in most of my potassium carbonate, hoping that such a big excess will force all the water to stick to it. I then left everything to stir overnight, and when I came back in the morning, I was more than relieved. The gigantic amount of potassium carbonate seems to have absorbed most of the water, since the volume of the ethanol layer was now more or less what I would expect. Also, not all of it dissolved, forming a thick slurry, which was a good sign. Now, I didn't want to separate the layers using my funnel, since it would probably clog, and to get my ethanol, I just poured the top layer into a cotton filter leading right into a distillation flask. I then assembled this flask into a simple distillation apparatus, and after a few minutes of heating, the ethanol started boiling. I collected it in this glass bottle serving as a receiving flask, and even though this whole apparatus was quite sketchy, with me having to glue my broken condenser together again, the distillation went really smoothly. When most of the ethanol boiled over and the liquid in the boiling flask got weirdly yellow, I decided to call this a day and stop the distillation. Apart from this heavily contaminated yellow junk, which confirmed that doing this whole extraction was well worth it, I was left with about 100 ml of some beautiful concentrated ethanol. It should be around 90% pure, and while this is actually plenty for making the vinegar, I wanted to dry it even further, preferably without much more active work, and the best thing to use for this are those cute little clay beads called molecular sieves. I think that upon hearing such a fancy name, no one imagines its bearers to be some random clay balls, but to a chemist, those balls really are a big deal. You see, on the molecular level, they are made of tiny little cages with openings so small only water molecules can enter them and get trapped, which dries the surrounding solvent and is perfect for situations like this one. Now, what's even better is that these sieves are reusable, and I've actually used these ones before a few times, so to activate them again I have to dry them. The best and easiest way of doing this is just microwaving the hell out of them, and for this I got them all into a glass dish and put everything into my microwave. Now, this is my food microwave instead of the usual chemistry one, but since this is the only one I currently have access to and molecular sieves are generally safe, I figured everything will be okay and turned it up to 900 watts. At first, a lot of water started evaporating from the sieves, which was really nice, and since everything seemed fine, I left this thing to work for 10 minutes. Now you can imagine my surprise when upon coming back I found my microwave smelling funny and the sieves glowing red. This thing turned out to be powerful enough to warm the sieves up to well over 1000 degrees Celsius, and I have never imagined that something like this would happen. I hoped that only a part of the sieves got destroyed and I could still recover some to use for drying my ethanol, and after allowing everything to cool down to room temperature, it was time to recover the dish and assess the damages. One problem, however, was that the dish managed to literally melt into the microwave's glass pane, and removing it also made me have to remove the pane, which financially speaking isn't ideal. Anyway, after the world's most intense drying step, apart from this blob of molten clay I will call the molecular sieve squared, I also have some beyond bone dry molecular sieves, which even though a part of them got deep fried, should be more than enough to dry my ethanol with. I got them all into the ethanol bottle, and those cool tiny bubbles started to appear almost instantly, signaling that the sieves were indeed working, since all this escaping air had to be first displaced by water. To allow the sieves to do their job, I left everything to sit undisturbed for a few hours, and when I came back the bottle's contents looked pretty much the same as before, except the ethanol now being a little cloudy because of some clay dust released by the sieves. It won't really matter for making the vinegar, but me being the purity-chasing chemist I am, I decided to filter my ethanol to get rid of the dust. This, of course, didn't do anything, and even made my ethanol take on a slight pink hue, since my vacuum filter is contaminated with an incredibly uncleanable dye I've made for a previous video. It's just such a chemistry moment when your purification attempt makes your product even dirtier, and it was at this moment that my patience reserves vanished and I decided to screw distilling this thing again and went straight to measuring its concentration and yield. When it comes to how much water I managed to remove, based on the density of my ethanol, it's now roughly 93%, which isn't too bad honestly. I mean, it's nowhere near 100% ethanol, but after all these struggles, I'll take that. The amount also isn't all too bad, and 67.7 grams of quite pure ethanol made from vodka is well okay. Nonetheless, this is still a trash method for concentrating ethanol, and I hope that nobody with drinking the end product in mind will try to repeat it. Anyway, with this very well earned ethanol ready, I can finally make some vinegar, and for that I have to let my chromium trioxide out of its confinement jar. In total, I need around 75 grams of it, and while I do have roughly this much of my homemade fork-derived stuff, I didn't really want to use it all for one reaction, so I weighed out only 50 grams of it straight into a flask and added in 25 more grams of some store-bought chromium trioxide. This will make the final mixture still contain a good amount of corrupted remains of some innocent forks, and the store-bought chromium trioxide just serves to make the scale of this whole process a little more comfortable. Anyway, with all the chromium trioxide safely in the flask, I can move on to measuring out all the other ingredients of this wicked cocktail, and the second one I have to add is distilled water. This whole reaction requires a relatively specific amount of it, and that's one of the reasons why I wanted to dry my ethanol as best as I could. I slowly poured 150 milliliters of distilled water into the flask, and this nicely made all the chromium trioxide stuck to its walls fall down, restoring my inner peace a little. With this forbidden juice ready, I now have to acidify it with a bunch of concentrated sulfuric acid, and I can't just pour it straight into the flask, since upon quickly combining with water, it can generate so much heat that it starts to boil, and in this case it would be just disastrous. That's why I assembled my flask into this fancy apparatus, which consists of a cold water bath with stirring and a funnel that will serve to slowly add the acid into the chromium trioxide solution. To start the addition, I charged the funnel with 75 milliliters of concentrated sulfuric acid and started adding it dropwise into the cooled reaction flask. Due to all my safety precautions, this addition went incredibly smoothly, and after a few minutes all the acid was in the flask. What's really interesting is that some red solid appeared in the solution, and this was just some reprecipitated chromium trioxide, which has a tendency to crystallize from cold and strongly acidic solutions. Anyway, this acidic and ultra-deadly chromium trioxide solution is professionally called the Jones reagent, and it's able to oxidize many organic molecules. In my case, the oxidized molecule will be ethanol, and to combine it with this red mixture, I can't just pour it in, since we all know what happens then. To not anger the chromium trioxide, I first have to dilute my ethanol with something, and since I can't really add any more water, pretty much the only thing that works is acetone. It's often used as a nail polish remover, and it is one of the very few things somewhat resistant to chromium trioxide. To prepare the required solution, I mixed 75 ml of it with 25 ml of my homemade ethanol, and then poured the resulting mixture into my extra fancy addition funnel installed in place of the first one. Before starting the addition, I also got some fresh ice-cold water into the water bath so that it will absorb more heat, which the reaction is said to generate a lot of. When everything was ready, I lightly opened the funnel's valve and began dropwise adding the acetone-ethanol mixture. This addition is usually done in a reversed order, with the chromium solution being added into the acetone solution, but to avoid messing around with chromium even more, and because I kind of forgot, I ended up adding the acetone-ethanol mixture to the chromium solution. Anyway, upon heating the chromium solution, the ethanol-containing drops made this weird sound, which was probably caused by a part of them instantly boiling from the heat of the reaction, and this was a little concerning. Nonetheless, everything seemed fine, and in terms of what's going on here, the sulfuric acid allows chromium trioxide to stick an oxygen atom onto the ethanol, oxidizing it to acetic acid and generating some chromium sulfate as a byproduct. On the molecular level, this whole thing is a little more complex, with the chromium first turning ethanol into something called acetaldehyde, which then gets turned into acetic acid through the action of sulfuric acid. Also, this is a typical redox reaction that fidgets with oxidation states of nearly all its ingredients, and if you want to know more about that, I've explained it in a little more detail in my previous video. Anyway, all these chemical conversions together produce a ton of heat, which is why I need to cool everything down using the ice bath, and at first it seemed to work well, until this happened. No. No, please, no, please. Oh. This was the closest thing to a chemistry-induced heart attack I've ever experienced, and I really have to thank the chemistry gods for not ruining this whole project and giving me the biggest cleanup of my life. Never in a million years did I anticipate this reaction to be so stupendously exothermic, and just a few milliliters of ethanol were enough to make a bunch of water go from being ice cold to boiling. It's really good that I did this whole thing in my fume hood, so that if it decided to boil over or explode I would still be safe. Nonetheless, I wasn't really feeling confident to continue the ethanol addition with this puny cooling system. That's why, after a bunch of trial and error, I made this beast of a water bath with constantly circulating ice-cold water, which will definitely be enough to tame the chromium and prevent more incidents from happening. When the flask cooled down enough, I started dripping in the ethanol once again, this time even slower, and this very cautious method seemed to work quite well. I watched the flask closely during the whole addition, and fortunately nothing weird seemed to happen. When all the ethanol was added, I noticed that the reaction mixture became this weird slurry, which probably meant that I'd cooled it down enough that some byproduct started precipitating out. I left this chromium slurry to finish reacting overnight, and when I came back the next day, it took on a little brighter green-blue color. I got it out of the water bath to take a closer look, and instead of a red mutagenic drink, I now had a greenish toxic slushy. This slushy hopefully contains a good bit of acetic acid, and to separate it from all the other junk, the only real option is distilling it off. For that, I assembled this flask into a simple distillation apparatus and started heating it, which made the slurry dissolve and left me with this dark green solution. Now, there are quite a few liquids in this funky potion, and they are going to distill in order, starting from the one with the lowest boiling point, which in this case is acetone. It boils at only 56 degrees Celsius, and indeed came over first. To separate all my product from it, I have to closely watch for when it stops coming over, which should be quite easy, since water, which should come over next, boils at 100 degrees Celsius. Now, acetic acid boils at 118 degrees Celsius, which in theory would allow me to separate it from water, but in practice the fractionating column required for that would have to be the length of the Eiffel Tower. This will make me have to do an extra purification step to get some pure acetic acid. Anyway, when my sixth sense figured all the acetone came over, I swapped the receiving flask to collect my product. For some reason, it turned light pink upon reaching this new flask, and at first I had no idea what happened here, but then I remembered that I used this flask for the fluorescent dye project, and even after numerous washings, a tiny bit of it still remained and dissolved in the acetic acid. I mean, the chemical resistance of this dye is beyond remarkable and makes half of this project pink. Anyway, the water-vinegar mixture kept distilling for quite some time, and when the distillation was nearing its end, my chromium slushy turned into some bubbling green sludge. It looks like some forbidden soup and consists mainly of chromium sulfate along with a bit of sulfuric acid, which has such a high boiling point it can't really escape the boiling flask. Also, even though chromium sulfate is a salt, meaning that instead of forming this thick liquid it should turn into some crystals, like many other chromium salts, it doesn't really want to do this for some reason and would much rather turn into a weird tar. Now, tar is an ever-present part of organic chemistry, often forming with each reaction, but this organic tar is always black or brown, and seeing some inorganic green tar is a really new thing for me. I mean, after doing chemistry for so long, I thought that I had seen all tars have to offer, but this project is unlike all the others, even when it comes to just how funky are its byproducts. Since this is no normal tar, I can't just pour it down the drain and need to properly dispose of it, which in this case will be just safely storing it until I decide to use it for something. For that, I first have to somehow get it out of this flask, and in this case it isn't actually that hard, since this uncommon tar is really soluble in water. I also need to choose a container to store my watered down tar in, and for that I decided to decapitate a water bottle, which includes removing all the labels and the weirdly annoying European Union cap. I then got this bottle into a very amateur chemistry filtering setup and passed my tar solution through it, which serves to remove any solid impurities and makes my tar extra pure. When everything passed through the filter, I removed my designer tar containment unit from it and labeled it appropriately. It will now just sit at the back of my lab for an undisclosed amount of time, which isn't optimal but still much better than just pouring it all down the drain, and such waste management is really important when you run an amateur chemistry lab. Anyway, now with the tar dealt with, I can return to my more important distillation product, which is this nicely pink acetic acid solution. As I've already said, I want to get some pure acetic acid from it, and since distillation is out of the question, I have to use a little more novel approach. I first have to separate all the acetic acid from water, and this is best done by converting it to a non-volatile solid from which the water can easily evaporate. Since acetic acid is, well, an acid, it can easily be converted into a solid salt through the addition of a base in a neutralization reaction. The base that I've decided to use is this innocent white powder called sodium carbonate. It's actually a very common chemical closely related to baking soda and will be perfect for this reaction. To start, I got all my pink acid water into a beaker with magnetic stirring and prepared a solution of sodium carbonate by mixing a random amount of it with some distilled water. Upon adding this solution into the beaker, a ton of bubbles appeared. In this reaction, acetic acid and sodium carbonate basically annihilate each other to produce a salt called sodium acetate along with some water and a metric freak ton of carbon dioxide. Now, the carbon dioxide bubbles can be a real pain since they often just randomly decide to turn into a volcano, but in this case I actually want them because when they stop forming I will know that all the acetic acid reacted and I don't need to add excess sodium carbonate, which would screw things up later on. Anyway, this reaction also made the pink dye disappear for some reason, which I guess is nice. Also, now that the bubbles stopped appearing, it's time to get my sodium acetate out of this solution. For that, I just used my hot plate to boil out all the water, which in the end left me with this moist sodium acetate powder, and to truly dry it, I have to melt it down. Now, salts usually have extremely high melting points, but sodium acetate is an exception with a melting point of around 300 degrees Celsius, which should allow me to melt it using just my hot plate. To make everything go faster, I covered the sodium acetate beaker with some aluminum foil, which traps some more heat in, and after a few minutes a small puddle of molten salt appeared in the beaker. I now have to cool it down to get my solid sodium acetate back, and if I just turned off the heat and waited, it would all solidify into an incredibly hard brick, so to prevent that, as the sodium acetate solidified, I constantly stirred stirred it using a metal spatula. This ended up producing a nice and fluffy powder, which was exactly what I wanted, and after letting it cool down to room temperature, I weighed it to see how much I've managed to make. It turns out that after all this struggle, I have nearly 29 grams of some reasonably pure sodium acetate made from vodka, and this yield actually kind of surprised me. Based on the amount of ethanol I've added, which was actually lower than I could have added due to a small mistake, the yield is still around 85%, which proves that this whole show of a project is somewhat worth it yield-wise. Anyway, to turn my sodium acetate into acetic acid with a good purity, I have to beat the acetate part of the sodium, and this is best done using a strong acid. The best acid to use for this is of course sulfuric acid. It is both strong and water-free enough to make all this work, and this is hopefully the last time I have to use it, since this whole chromium project must have consumed like 2 liters already. To safely combine it with sodium acetate and simultaneously distill the created acetic acid, I assembled this upgraded distillation setup with both a slot for an addition funnel and a condenser. To start the reaction, I first installed my addition funnel pre-filled with 20 ml of concentrated sulfuric acid and started to slowly drip it into the sodium acetate flask. Upon contact with sodium acetate, the sulfuric acid doesn't seem to do much, but on the molecular level, it's beating the sodium acetate apart, giving it a hydrogen atom to form acetic acid and itself becoming sodium sulfate. Now, this reaction proceeds in 2 stages, with the first one resulting in the formation of something called sodium bisulfate that upon heating can react with more sodium acetate, and before I remembered that, I kind of freaked out. I added only half the required sulfuric acid. The advantage of this whole method over other ones is that the only volatile product it makes is acetic acid, and to recover it when all the sulfuric acid was added, I replaced the addition funnel with a stopper and wrapped the apparatus in some aluminum foil to make it easier for the acetic acid to distill. It actually came over way faster than I expected, and only a few minutes after starting to heat the flask, a bunch of it already made its way into this cute little receiving flask. Along with acetic acid, this distillation also makes a ton of this white mist, which looks really cool and mysterious, especially in the condenser. Anyway, because of the surprising speed of this distillation, after just an hour, I was left with quite a bit of some nice and clear acetic acid. Apart from it, I also had this solid cake of sodium sulfate in the boiling flask, which I ended up dissolving and pouring down the drain, which in this case I could actually do. Anyway, the amount of acetic acid this distillation left me with is quite alright and roughly what I expected. In terms of the exact yield, I managed to make 19.8 grams of roughly 95% acetic acid, which at such high concentrations is also called glacial acetic acid since it freezes at quite a high temperature of about 16 degrees Celsius. Also, for the third damn time in this video, the pink dye came to haunt me, since it turned out that some unbelievably small amount of it was on my receiving flask's glass joint and dissolved upon contact with acetic acid. This makes it look a little impure, but I honestly don't care. I spent so much time and effort making the chemicals required to make those glorious few milliliters of some extra strong and smelly vinegar.
Oh, Jesus.
And after all this, I was just happy that I managed to do it. Now, for a fitting end to this whole series, I decided to do the only right thing and make some actual vinegar using my home-brewed acetic acid. To do that, I got 10 grams of it into a flask and diluted it down with around 90 milliliters of water, resulting in a dilute acetic acid solution or just vinegar. It smelled exactly the same as the stuff you can buy in a store and made a good dressing for this very sad salad, which I unfortunately won't eat, since a good grudge to follow is to never ingest anything that touched chromium trioxide. Anyway, this 3-episode multi-month project has been a real ride for me. I mean, I've learned a ton and got to experience so much wonderful chemistry, all of which started from some forks marinated in acid and then transformed into some forbidden Cheeto dust and a deadly cancer powder, only to turn vodka into vinegar. It's projects like these that really make chemistry seem like magic, and it's what makes me love it so much. Also, on a more personal note, I plan to take a 2-month break after posting this video, since I've been recording videos every 2 weeks for literally half a year. It's a really big amount of time when I say it out loud, and I just want to have some time to get back to doing some more relaxing things like playing with my wonderful cat. However, don't worry that I am disappearing from YouTube or got burnt out, since for the next year I have a ton of some next level projects planned. Apart from that, I will also be starting a second channel for behind the scenes of my videos, because a lot of people have asked for it and I thought that it would be a cool thing to do. I've actually recorded this whole video with a second camera in hand while trying to talk in real time, and you will be the judge of how it went. Anyway, thank you guys for all the support you give me and for keeping this channel alive more than ever. Also, thank you very much for watching this video and the whole colorful series. If you enjoyed it, you can like this video, share it with a friend and subscribe to my channel. If you would want to further support my work and gain access to a lot of cool exclusive videos unsuitable for YouTube, I invite you to join my Patreon. Also, a big thank you goes to all my amazing Patreons for their support and allowing me to have the funds for all those projects, and see you guys in the next video.